Alrighty, so now I'm going to talk about section 2.4, which is numerical derivatives, or calculating the derivative numerically. And all that means is that you're finding the value of the derivative, or the slope of a tangent line, to a function at a particular point, at a particular x value. And that's always going to result in a number, right? So, you learned how to do it graphically. And I should have had this little graph ready, but I'm going to find one. All you have to do, so let me put the book here. So suppose, I want to find, I'll make this a little bit closer. Suppose I want to find the derivative, or the value of the derivative, at the point where, I'm trying to find a convenient point, at the point where x is equal to 1. Okay? At that instant in time, what is the slope of the tangent line? Now I could draw a little tangent line and eyeball it and say it's about -1, but we really want to be more precise. So what you learned before in the previous sections is, you take a point, this is the point in question. I don't have a pencil. Oh, I do, good. I was going to say, I don't want to write in the book because I don't have my pencil, but... Okay, so this is the point in question. I want to know what is the slope of the tangent line, what is the instantaneous velocity at this point, or what is the numerical derivative. They all mean the same thing, okay? So what you did was you found a point a little bit to the left, and you computed a little secant lines, the slope of a secant line there. And then you found a point a little bit to the right, and you connected those two, which formed a secant line, and you computed that slope. And then you added the results together, divide by 2, and that gives you a pretty good estimate of the slope of the tangent line in that case. Right? So we should all be good on that. That should be easy. The other way you could do it is you could actually get out a straight edge and, use this point 1, 0, and draw a tangent line that looks like it goes through some convenient crisscross in the grid, some perfect number like 0, 1. 0, 1. And by the way, I meant -1 when I said the slope of that. And then you can compute the slope that way too, and it's going to be pretty accurate. Alright, so you can either average little secant lines that are very, very close to the point in question, or you can take a ruler and, extend your line from that point to some convenient point on the grid and estimate it that way. But it's pretty much the best you can do. It's a good estimate. It may not be dead on accurate, but it's probably going to be close enough. So then you had the numerical, meaning in a table, right? So this was number 10 from page 106, just in case you're interested. And you had to fill in the missing pieces in this table with derivative value. And I went over this one in class, so I'm not going to go over it again, but the idea again is you can either draw the tangent line or take the average of 2 secants to get these values and fill in. And this one would be hard too, because as you can see at 0 it's like -0.7. So he's being really accurate because he knows what the function is. For us it would be pretty difficult, alright? But we could get a pretty good estimate, even though it's not perfect or as accurate as what he's got here, by averaging little secant lines to the left and the right of that point, or extending a tangent line out till it goes through some convenient point in the graph. But rather than that, what we really want to look at is the calculator, because the calculator can do wonderful things, and it can give us a numerical derivative that we need. So the first way you can do it, the easiest way, if you just need the quick slope of a line, you can do it right from your home screen. Press Math 8, okay? So some calculators it's going to say n-deriv, which is fine. And if your calculator does say n-deriv, just as a side note, it'll look like this with a parenthesis. You need to put your function in first, followed by a comma, x comma and then x, so you wouldn't type in x equals, but you would say something like, 5 or something. So I've got my other calculator here, and I'm going to go ahead and put it in classic mode just in case you don't have math print on yours. Alright, so let's start with this calculator because it's already set up. Always in this calculator, so whether it's from the home screen or if you're in Y2 or Y3, something like that, this will always be X here, and this will always be X. Sorry, we're going to find it at a point. Sorry. So let me delete that. You need to input your function. So let's put in, I don't know, 2x squared minus 3x minus 4. Put your function in. Go over here and let's say we want to know what is the slope of the tangent line, what is the velocity, what is the instantaneous rate of change of this function at the point where x is equal to 2. So see, instead of putting x in here, I'm putting the point which we're curious about. And press enter. And the slope is 5. Now, just to show you something, so those of you who know the power rule, if the function, what was it again, 2x squared minus 3x minus 4, this was the function. If I take the derivative of that, it's 4x minus 3. So if I evaluate this derivative at x is equal to 2, that gives me 4 times 2 minus 3, which is 5. I get the same answer as my calculator gave me. In other words, whatever this function looks like, and we're going to see it in a second, I know it's parabolic or quadratic, the slope of the tangent line is going to be pretty steep. It's going to be a 5 at the point where x is equal to 2. So you can do it from the home screen, which is nice, or you can do it two ways from the graphing screen. So I'm going to put this in here. In y1. Now I want the numerical derivative. The first way I can do it is I can just put the function in y1 and hit the graph key. By the way, always make sure you're in radian mode in calculus. Okay, so there's my graph. I know what it looks like. I know I have a bump here, so that's going to be a critical number on the graph of the derivative at about x equals to 1. But I want to know what is the slope of the tangent line when x is equal to 2. How steep is that thing? Right? So I can do second program key, so that's the second draw menu. Number 5 is tangent. And now I need to tell the calculator at what value of x. So at x equals, just press 2 and enter. And not only will it draw the tangent line to the point where x is equal to 2, it'll give you the equation, and in that equation, since it's y-intercept, slope-intercept, is going to tell you that the slope is 5. So we got the same number yet again. Another way you can do it, so let me just clear that drawing and keep the original graph. Another way you can do it is you can go to y equals and go down to y2, say, and press math 8. Again, we put an x here. To put our function in here without having to retype it, you press vars right arrow 1, 1. So again, you're telling the calculator, I want the derivative of the function that's sitting in y1. And you can go over here and you press 2. Okay? And hit graph. And look at this. You get a constant function. But it's not that the function's constant. It's giving you the height or the slope of that derivative at x equals to 2. It's 5, right? It's y equals 5, or y prime equals 5. So that's another way you can get it. It's just going to draw a horizontal line through whatever that derivative is going to be, the slope of the derivative is going to be, or sorry, the slope of the tangent line is going to be at some particular point. If I clear that drawing, oh shoot, sorry, I didn't mean to do that. So it's going to redraw. Let's give it a second. Super slow. Okay, so it's done. Go back to y equals. You know, maybe I want to know what the derivative is at x is equal to 1, so I'm assuming it's probably 0 there. It looks like at x equals to 1 from the graph that I would have a horizontal tangent line, so let's just see if it's true. Alright, there's a bump, so I should have a 0 there, and it looks like it's at 1. Ooh, look at that. Our answer is going through the line y equals to 1. So the derivative, or the slope of the tangent line, or the instantaneous velocity or instantaneous rate of change at the point where x equals 1 is 0. It's saying 1. So maybe that bump's not quite where I think it is. Okay? So those are the two ways. I would say I wouldn't go through all this. To be honest with you, I would not put in an end deriv here if I'm just looking for a numerical slope. I would just hit the graph key and do second draw 5, and because that's going to give you the equation and the slope right there. Okay? So again, from the graph screen at second program or second draw 5 at x is equal to, we said 2, and to me that's simple enough, plus it gives me the equation if I need it for some other part of a question. Okay, so that's the numerical derivative. It's just a number, and it's being evaluated at a particular x value at a particular point on some function. That's all it is. That's all 2.3 is about. You know, is the slope of the tangent line 1? Is it 5? Is it 0? Is it -2? What is it? That's it. So those two programs should come in pretty handy. The other nice part about this section too, if you want, is in the exercises on page 112, like 1 through 6, they give you functions, and some of the functions are pretty crazy little functions. So for example, like x ln x, right? So x ln x. And we want to know, so I'm going to graph that. And they're asking you to find the derivative when x is equal to e. And he's telling you to use end deriv. Well, I wouldn't. I would say second draw 5 and x equals to e. Well, that's just the second division key on your calculator. Second divided by. And you see it puts x equals to e in there, and hit enter. And it's going to graph your tangent line. And it's going to tell you right away that the slope is 2. So if you come out with 1.99999, it's 2. Okay, the slope is 2. That's it. Or, again, if you wanted to, you could do that from the home screen. You could say math 8. You could put x. You could type in x ln x in there. And then when x is equal to e, so second division key, and do that, and it's going to give you the numerical slope of 2. Okay, so you can use end deriv, or you can use that equation of the tangent line, and you're going to get the same answer either way. So that was section 2.4. Done. Okay, I almost forgot. So, for those of you who have the TI Silver Plus, and you go to mode, and you scroll up, and you don't have this math print, or you put it in math print and you can't get the math print, that means you're in classic mode and you need to change your operating system, which I can do for you, but I gotta wait until the tech people install this program that I need on the work computer. So anyhow, we're in classic mode and we put a function into y1. Now, when you go to y2 and you press math 8 and deriv, you see it stays like that. You don't have the little boxes where you put the x's and the numbers and whatever. Piece of cake. So I want the derivative of the function in y1, so I can press, move this up a little bit. Sorry. So I'm going to press vars, right arrow, 1, 1. That means the function sitting in y1 is I'm going to take the derivative of, right? comma, don't forget your comma. Derivative with respect to the variable x always, comma, derivative with respect to the variable x, close the parenthesis, and hit graph. Now the bummer on this calculator, while it's a great calculator, I used this one for many years, is that the graphs aren't in color. So after a graph or two, this one's easy enough because we went from a quadratic to a linear function. It's not too crazy, but you know, sometimes these functions are crazy, and when you graph on top of that, it gets like if you graph the sine, the derivative of the sine is the cosine, and it kind of like all looks the same. It's craziness. So it is more difficult to differentiate, no pun intended, between the graphs the more complex the function is. But in this case here, I've got my derivative, which is 2x squared minus 3x minus 4, my function, which is 2x squared minus 3x minus 4. I can clearly see that my function is decreasing from negative infinity all the way to about 1, which means my derivative should be below the x-axis, and then it increases from about 1 to positive infinity, so my derivative graph should be above the x-axis. I also have a minimum here, or a bump, which means that that's going to project as the 0, the critical number on the graph of the derivative. Okay, so you can still compare the graphs. If you want to shut one off, you can press y equals, and say you want to turn off the graph of the original function, just arrow over to the equal sign, press enter, and arrow back over, and you see it's not highlighted like that one. So when you hit the graph key, it's only going to say graph the derivative, if that's what you're interested in looking at, and it won't graph the original function. Okay, or vice versa. You could shut the derivative off and graph the original, however you want to do it. From the home screen, it's the same way. If I want, before I go to the home screen, so let me turn that graph back on. Let me shut nderiv off. And if I graph my function, and again I want a numerical derivative, say at x is equal to 2, right? X equals 2. Then I just do second program key, 5, which is tangent, and I tell the calculator 2 enters, and it'll draw the tangent line to the graph at x equals to 2, and it gives you that slope of 5. If I want to do it from the home screen, so same thing as the other calculators, just you don't have the nice color. If you want to do it from here, you can press Math 8. And again, though, the problem is you got to put the function in. So 2x squared minus 3x minus 4, okay, comma, derivative with respect to x. So x is always in the second place there, comma. And then we wanted the derivative when x is equal to 2. Close the parenthesis, and there's the slope, 5. So you can do that on either calculator. Same thing. It's just if you're on classic mode and you can't get off it, or you don't have that math print program on there, then it's going to say nderiv instead of have the little derivative notation, a Leibniz notation like the other calculator. Capiche? Have a good night.